the structure for enhancement type MOSFET is exactly same as of the depletion type MOSFET. These will be to N plus material, and this P type substrate will be grounded. This would be the gate terminal, source terminal, and drain terminal. Remember one thing, that there will be no channel in case of enhancement type MOSFET. We will have to create a channel between source and drain terminals by applying proper biasing. So before applying biasing, there will be a depletion layer on both the sides. Now when we apply biasing to this type MOSFET, uh, we will have to take care of this, that the source terminal, which is now grounded, the source terminal and the substrate, this terminal will be called as body terminal. These two terminals must be kept at either same potential, or we will apply some potential difference, but that can create problem in the operation. So as source is N type material, body is P type material. If body is at higher potential with respect to source, then this junction will be forward biased and conduction will start through this junction, which is not required, which is not a desired for this operation, for the operation of this enhancement type MOSFET. So for this purpose, if we are keeping this source as at ground terminal, at ground potential, then this body should be always ground, so that there will be no potential difference between source and body. And if we have some negative potential with us, then connect this body terminal with the negative. So I will say that the body terminal should be connected to the most negative potential available. So if we have some negative potential, then connect this body terminal to this negative potential, negative battery negative potential, so that we will ensure that there is no uh, positive potential difference between source and body terminals. So now we will bias this enhancement type MOSFET. If we want conduction in this type of MOSFET, then we will have to create a channel between source and drain terminal. Means from source to drain there should be a channel, so that conduction can start in this type of MOSFET. If we apply a negative potential to this gate terminal, then the potential of gate with respect to body will be negative, and for this negative potential the holes will be attracted here in this region, and these holes are of no use in this region because we want an n channel in this region. So for this purpose we will not apply this negative voltage here. So instead of this negative potential we will apply a positive potential to the gate terminal, and this voltage will be our gate to source voltage VGS. Now uh, we apply some positive voltage to the red terminal, and this voltage will be our drain to source voltage VDS. Now we will start the operation and we will draw the characteristics of this MOSFET. First, if we keep VGS equal to 0 volt, then with this VGS equal to 0 volt there will be no electrons attracted in the channel region. As no electrons attracted in the channel region, we will say there will be no channel in this particular region. If there is no channel in this particular region, drain current ID will be equal to 0. And if drain current ID equal to 0, we'll say this MOSFET is in cutoff, not operating in cutoff. This cutoff mode we didn't say in depletion MOSFET and in JFET. In both the cases, we saw that when VGS equal to 0 volt, sufficiently large current was flowing, that is IDSS. But in case of enhancement type MOSFET, there is no channel between source and drain. So unless and until we apply proper biasing, proper gate to source voltage, there will be no channel and there will be no conduction. That is ID will be 0. Now in the second case, we will apply a positive VGS. This positive VGS will keep it less than threshold voltage VT. And in the last case also we saw that threshold voltage VT is that voltage for which the inversion layer can form. So if applied VGS is less than VT, again there will be no inversion layer form in this region. If there is no inversion layer in this region, again drain current ID will be equal to 0. And again this MOSFET will be in cutoff. Third case, if we apply VGS which is greater than or equal to threshold voltage VT, then this voltage is sufficient to attract these electrons in the channel. If VGS is applied greater than threshold voltage VT, then these electrons will accumulate in this region and a channel will be created between source and drain terminals, between source and drain terminals, and this will be the depletion layer. A region with large number of electrons will be created. This is inversion layer, and due to this inversion layer a channel is created between source and drain terminal. So when VGS is greater than equal to VT, then only it is possible for the enhancement MOSFET to conduct. So in this case we will draw the transfer characteristics of enhancement type MOSFET. We have applied a positive gate to source voltage and we will uh, note this drain current ID. So when VGS equal to 0 volt, with VGS equal to 0 volt, there will be no channel between source and drain terminal, hence drain current ID will be equal to 0. When positive VGS is applied, Drain current ID will again be 0 if VGS is less than threshold voltage. And if VGS is greater than threshold voltage, the channel will be created and current will flow through the device, and we'll get a graph like this. This will be the transfer characteristics for enhancement type MOSFET, and this is the threshold voltage VT. Threshold voltage VT. Now we will draw drain characteristics for this MOSFET. For this purpose, we will have to keep this gate to source voltage greater than threshold voltage, so that the channel will be there in between source and drain terminal. When VDS is applied, a field will be there in the channel, and this field will be responsible for the conduction. First case, when VDS equal to 0 volt, when VDS equal to 0 volt, this is the MOSFET. When VDS equal to 0 volt, this drain terminal will be grounded, and we have already grounded this source terminal, and also body is grounded. This source to body, drain to body, both the terminals are grounded, so there will be no reverse biasing. In this case, source to body has no potential difference between source and body, there will be no reverse biasing. So in this case, the channel between source and drain will be almost flat. Flat means width of channel from both the ends, from drain, from source, will be same. So when VDS equal to 0 volt, there will be a flat channel between source and drain terminal. But when VDS equal to 0 volt, the field in the channel will be equal to 0, and hence drain current ID will be equal to 0. We will draw now drain characteristics between VDS and ID. Drain current ID will be 0. Second case, now we will apply a positive VDS. VDS is greater than 0 volt. When VDS is greater than 0 volt, there will be an electric field in the channel. And due to this electric field, the electrons will start flowing from source to drain and will contribute a drain current ID. For small values of VDS, the field will be small and the drain current ID will be small. With increase in VDS, the drain current ID will be increasing. But at the same time, when VDS is increasing, for example, if we apply positive VDS, then this will be at positive potential, this is at zero potential. So N type material is at positive potential, P type material is at zero potential. So there will be a reverse biasing between drain and source, and due to this reverse biasing, the depletion layer will penetrate more as compared to towards source end. As this depletion layer is penetrating more, the channel width from the drain end decreases. But at the same time, with increase in VDS, field is increasing, so drain current ID will be increasing. With further increase in VDS, we will see this shape of channel. Channel will be like this. Width of channel will be decreasing from towards drain end as compared to towards source end. But at the same time, the field which is due to VDS is increasing, so drain current ID will be increasing. Now at a particular voltage VDS, the channel width will reduce to zero near drain end. This point is called pinch off point. This voltage at which the channel width reduces to zero near drain end, this voltage is called VDS equal to VDS SAT, and it is equal to VGS minus VT, threshold voltage. So when channel width reduces to zero near drain end, at this point there is no channel near drain end, but at this point this electric field in the channel becomes very strong, and this electric field will maintain a continuous flow of electron through this region. The electrons will start from source and flow up to pinch off point, and from this pinch off point will be dragged to the drain terminal by this electric field E. So drain current ID will continue to flow. At this point, when voltage is VDS SAT, which is equal to VGS minus VT, at this voltage this drain current ID will saturate in this region, in this MOSFET. Further increase in VDS above VDS SAT will decrease the length of the channel. Now pinch off point is shifted here, pinch off point. Again operation will be the same. The electrons will start from source, travel up to pinch off point, and from this pinch off point these will be dragged to the drain terminal by this electric field, and current will continue to flow. This will be the characteristics for enhancement type MOSFET. If we change this VGS, we will get different curves like this. This is called ohmic or linear region, and this is called saturation region. So it is operating in both the region, linear region and saturation region. In the ohmic region, we can see that the graph is a straight line. See, if we have a resistor and if we apply a potential across it, and if we note the current I through this resistor R, then if you draw characteristics between I and V, voltage V, then the characteristics will be a straight line. Characteristics will be a straight line. So we can say that if VI characteristics of any device is a straight line, it will be resistor. So in ohmic region of operation, it behaves a resistor, like a resistor. A MOSFET in ohmic region behaves like a resistor, or more specifically we will say as voltage variable resistor, because we are getting two different curves for two different values of VGS. If we change VGS, the curve will change. If the curve is changing, means resistance is changing, so it is voltage variable resistor in the ohmic region. While in saturation region, we are getting a constant curve. This curve is constant current curve. VDS is changing, but drain current ID is constant. If drain current ID is constant, we will say that in saturation region it is operating like a current source, and more specifically we will say as voltage controlled current source. So in saturation region, a enhancement type MOSFET behaves like a voltage controlled current source. So in Enhancement type MOSFET, initially there was no channel. If proper VGS is applied, then only channel will be created, and if the channel is created, the device will start conducting. Now we will see the current equations for enhancement type MOSFET. First, cutoff region. If it is operating in cutoff region, then VGS should be less than VT. If VGS is less than VT, then it will be in cutoff, and if it is operating in cutoff, then drain current ID is equal to 0. No conduction. Second, linear region. If it is operating in linear region, then VGS should be greater than equal to VT, and VDS should be less than VDS sat, equal to VGS minus VT. So if VDS is less than VDS minus VT, VGS minus VT, that is VDS sat, the MOSFET will operate in linear region, and in the linear region, drain current ID is given by ID equal to mu n into C oxide into W by L into VGS minus VT into VDS minus VDS square by 2. In this equation, this term is called transconductance parameter. It is called transconductance parameter and written as Kn. Unit is ampere per volt square, where mu n is mobility of electrons, C oxide is oxide capacitance that we saw in MOS capacitors, and W by L is called aspect ratio, where W is width of channel. This width is this dimension. For example, if this is the MOSFET, if this is the MOSFET, these are the N plus region, and this will be the gate metal. So this dimension is called width of channel, and this dimension is called length of channel. The third case, saturation. If it is operating in saturation region, then this condition must be satisfied that VGS should be greater than equal to VT, and VDS is greater than equal to VDS sat, which is equal to VGS minus VT. So if VDS is greater than VDS sat, then it will be operating in saturation region, and in saturation region, drain current ID is given by 1 by 2 mu n into C oxide into W by L into VGS minus VT whole square. This equation is little bit more comfortable than the equation in linear region. Again, this is called transconductance parameter Kn. So we will say that ID is equal to 1 by 2 into Kn into VGS minus VT whole square. So we will say that ID is directly proportional to VGS minus VT whole square. So in saturation region, drain current ID is directly proportional to VGS minus VT whole square. Now the transconductance GM for enhancement type MOSFET. As in the case of JFET, the transconductance was del ID upon del VGS. Same will be the transconductance for enhancement type MOSFET, del ID by del VGS when VGS equal to constant, VDS equal to constant. Next, drain resistance, channel resistance RD, it will be same again, del VDS upon del ID at constant VGS. Now we will solve some problems